Hi, today let's discuss an important theorem about continuous functions. Let's begin our discussion by reviewing the definition. A function f is continuous at a if the two-sided limit of f of x as x approaches a is exactly equal to the functional value at a. I'd like to give you a visual to keep in mind about continuous functions. A is a point or a number on the x-axis, and if f is continuous at a, the definition tells us that same as saying the two-sided limit equals f of a. So if you pick points very close to a, or in other words the neighborhood of a, and look at a picture of the graph right above that interval, then you should see an unbroken curve like this. That would imply that limit of f of x as x approaches a, that is the two-sided limit, is exactly equal to f of a. So this is the definition that we will be using in the theorem that we're about to discuss. You will need to keep this definition in mind at all times. The reason for that is the minute we know f is continuous, we need to be able to translate that into this. That means we need to be able to say, oh, if f is continuous, it must be true that the two-sided limit is exactly equal to the functional value. Or conversely, if we know this piece of information about a function, that the two-sided limit at a certain point is exactly equal to the functional value at that point, that is implying that the function is continuous at a. So learn this definition, and now let's look at the theorem that I want to talk about. So continuous functions have some very nice properties. They're very easy to work with for several reasons. So it would be good for us to be able to spot continuous functions, and this theorem helps us. So let's look at the theorem I have. Suppose functions f and g are continuous at the point a and c is a constant number. Then the following functions are also continuous at a. So what it's telling you is, if you know some two functions are continuous at a, then it allows you to conclude that some of the new functions are also continuous. So let's look at number one, f plus g. That's a new function that we can create or build from these building block functions f and g. How do we do that? Well, recall f plus g is a function in this manner. It takes an input x, and the output it gives is f of x plus g of x. So remember that. So if you define f plus g in that manner, then what this theorem is telling you is, if you know f is continuous, if you know g is continuous, then in fact f plus g is also continuous. We're going to prove that in just a minute. And number 2 says f minus g is also continuous. 3 says c times f, this is a new function, that's also continuous. And 4 tells you, if you start out with two continuous functions and you create a new function fg, then this theorem is guaranteeing you that fg is also continuous at a if f and g are continuous at a. Similar statement about f over g. The only thing to be careful here is we do not want to divide by 0. So f over g is continuous at a as long as g of a is not equal to 0. Once again, f over g is a new function created from f and g. The way this function works is it takes an input x, and the output, you might guess, is f of x over g of x. So this is also continuous as long as g of a is not equal to 0. Now let's move on and prove why f plus g is continuous at a if we are given that f and g are continuous at a. So let's now prove that the sum of two continuous functions is also continuous. So the statement is, suppose f and g are continuous at a, prove that f plus g is also continuous at a. Remember, when proving such theorems, we really need to have the definition of continuity in our heads. So here's the definition to refer to. F is continuous at a really means that this equality holds true, which is two-sided limit is exactly equal to the functional value. So this is how we proceed. We are given f and g are continuous at a. We translate that information into, since f and g are continuous at A, that really means this statement is true. The two-sided limit equals the functional value. That's the statement about f. And g is continuous means this two-sided limit is exactly equal to that functional value. So this is given to us. We can use it anytime we want in our proof. Now, we want to prove f plus g is continuous. That means if we could prove this, then the two-sided limit of f plus g of x as x approaches A, if that equals functional value, then we're done. So notice here, I'm simply applying this definition modified to the scenario. Here my function is f plus g. So it's really this same one, instead of f, it's my f plus g. So two-sided limit of f of x, two-sided limit of my function f plus g, and functional value evaluated at A for this f plus g. So let's try to prove this on the other board now. Here I have the left-hand side of the equality I would like to prove. You'll notice this is the expression. We will do the work and arrive at this expression, which is the right-hand side of the statement that we want to prove. So let's proceed as follows. Limit of f plus g of x as x approaches A. The first thing I do is I think to myself, what is f plus g of x? Remember, this is a new function created from f and g. By definition, this is simply f of x plus g of x. That is, I'm using the definition of f plus g, how we created it. So from here, I go to the step. I've kept everything same. I use an equality sign. The only thing I have done is replace this with f of x plus g of x, because this expression is exactly same as this expression by the definition of f plus g. I'll continue on. At this point, I recall one of the limit laws, which tells us the limit of the sum of two functions is really same as taking the limit of individual functions and adding them together. So limit of this plus limit of this function. So if you want to justify how we move from this step to this step, we can simply say I used a limit law, which tells you the limit of the sum of two functions is the sum of the individual limits. That's what we used. Now how do we go from this step to this step? Remember, we were given f is continuous at A. If you notice on the other board, one of the first things we wrote down was, in that case, this two-sided limit is exactly equal to f of A. That's what it means to say f is continuous at A. So this expression is a number, it's exactly equal to this f of A. Same thing, plus is plus, and this expression, this two-sided limit, is exactly equal to g of A, because we're given g is continuous at A, and that's what it means. And again, I use equality signs. And here, f of A plus g of A. Another way of writing it is f plus g of A. This is really the definition of f plus g. F plus g is a new function, takes an input A and gives an output. What is the output? By definition, it is f of A plus g of A. So we've proved it. Limit of this function, the two-sided limit, is exactly equal to plugging in A into the function, so this functional value. So this proves that f plus g is continuous. Now we can prove the other statements for continuous functions in the same manner. So in other words, if you imitate the same procedure, you can prove that f minus g is continuous at A, the product of two functions is continuous, and also f over g is continuous where g of A is not equal to 0. Very similar procedure, you can do that. So I'm not going to prove that today. Just want to go back to the definition of continuity and remind you that I said somehow continuous functions are very nice to work with. So many functions that you know are in fact continuous. For instance, polynomial functions. In another video, I'll give you a list of most familiar functions that are continuous. In those situations, here's the reward that you will get. If I asked you to find a two-sided limit of a continuous function, you no longer need to create a table of values and all of that. Notice this theorem tells you if you're dealing with continuous functions, the two-sided limit is in fact equal to f of a. So it's as though you're just plugging in a for x, and f of a is very easy to compute. So if you have a continuous function and you have to find a two-sided limit, it is simply substitution. You plug in a for x, compute f of a, and f of a is the two-sided limit. So that's one of the ways we are going to use our knowledge about continuous functions to find two-sided limits. So we'll explore that in another video. Thank you.